Hello and welcome to this video about doing mathematics on a computer. In this video, we will learn how to make a computer program that can compute the nth derivative of the inverse cosine function. We'll need to calculate each next derivative from the previous derivative, so we'd need to store all of these derivatives in a table. If we needed to find the 100th derivative of this function, we'd need to have a table storing all of the derivatives from the first to the 100th. This program is very similar to the one in which I used to find the nth derivative of the tangent function, with only a few minor adjustments. So to make a start, we'll write out this equation containing the inverse cosine function. So this is the first derivative of this function, and it can be written out like this in indice notation, which makes it a lot easier to differentiate. We'll assign this variable u to be equal to this amount. Then we'll calculate the first derivative of u. And we can substitute u back into this equation and get the derivative of u as a function of u and x in this form, which is a very simple function to work with. And we can use this equation to very easily get the next derivatives of u. So then we can get the second derivative of u, using calculus rules and substitutions. This has two simple terms added together, so the nth derivative will be a long string of terms added together. So now to calculate the derivative of this expression, which will enable us to get any derivative of x's and u's multiplied together. We'll use the product rule to expand out the derivative of w to be this. Then this will be the derivative of w in its most simplified form. We'll use this to calculate the nth derivative of the inverse cosine function. So this will be the data structure used to hold all of the derivatives of the inverse of cosine. We'll start from the first derivative u and store this in the table first. Then we'll calculate the other derivatives from this first one. So this will be the algorithm for calculating the nth derivative of inverse cosine. In this table, we're up to the fourth derivative, and we need to calculate the fifth derivative from it. We'll use the formula for the derivative of w that we looked at a couple of minutes ago to get two terms for each term of the derivative, and then store them in the construction array. We'll start to simplify them by bringing like terms together. Then we'll perform a zero eliminate to get rid of all terms with 0 as their coefficient. This is the most simplified form of the next derivative. Then we'll place it into the table and place its position in the pointer table. So this is the function that we'll use to calculate the next derivative. We'll get the start and end positions of the current derivative. We'll make up a loop to look at every term in the current derivative expression. We'll get all of the constants from this table. Then we'll get the next constants from these current constants so as to build the next derivative. This is the main difference between the tangent derivative table and the inverse cosine derivative table. Then we'll place these constants into the construction array so as to simplify them before putting them into the main table. Then we'll increment this variable. It seems to be the same as j. We could have used j, but I like to make it look like the tangents equivalent function. We could multiply k by 3 and increment it by 2 instead of 1. Then we'll save the length of the expression in the construction array. So now to simplify this expression the first time by gathering like terms together, that is, terms with the same powers of x and u, which means that the values of m and n must be the same. So we'll make up the main loop to go through all of the terms in the construction array. We'll get the values of m and n for this current term that we're looking at. Then we'll make a second loop to look at all of the terms that are ahead of it. We'll get the constant term of each of these terms ahead of it. And if it isn't 0, we'll look at its own powers of x and u. And if these two terms have the same values of x and u, which are given by n and m, then we'll add the value of its coefficient onto the first term, and set the coefficient of the second term equal to 0, getting ready to delete it. So this is the zero eliminate function, which is nearly identical to the version found in the tangent function. We'll have 2 pointer variables in the array, and make a loop to go through the entire array. The second pointer or index variable j lags the main variable, creating a function that naturally deletes all of the zero terms, or terms with zero coefficients. So we'll get the value of the coefficient of the current term, and it can be 0 or extremely small. We'll make it positive here. And if it isn't 0, then we'll copy the values of this term into another position and increment the second pointer variable. This has the effect of deleting the term if it's equal to 0. And we'll set the new value of the length of this expression, because it most probably is smaller. It turns out to be always smaller, because the expression simplifies well. So the next step is to copy the expression in the construction array to the main table array. We'll make up a loop to go through every term in the construction array. And here is where we'll copy the content of the construction array to the main table. So here's where we'll put all of these functions together to create the table. We'll copy in the value of the first entry, which is u. And we'll set the number of derivatives found and placed into the table here. This variable will be used by other functions to calculate the contents of each entry in the table. So now to make a loop to get the rest of the derivatives in the table, like the second to the nth derivative. We'll call the construct the next derivative function to get an unsimplified next derivative and place it into the construction array. Then we'll simplify this expression to get the most simplified expression for the next derivative. We'll then get the pointer variables pointing to the position of this next derivative in the main table. Then we'll copy the expression from the construction array to the main table array. Then we'll increment the number of derivatives we've found so far, and this completes the table. So this is the main difference between the function to find the nth derivative of inverse cosine and the function to find the nth derivative of tangent. These constants are calculated differently. But we still have to test this table to make sure that it's correct. We'll print out a message that testing is in progress, and that the position in the table variable must be in range. We'll test it using numerical differentiation. We'll get the start and end of 2 consecutive expressions of derivatives in the table. We're testing one against the other. The first one should be the numerical derivative of the next one. So we'll make up a loop to test the expressions for a large number of input variables, up to 1000. Then we'll pick an input variable having a good range for inverse cosine, being 1 and -1. But not too close to 1, -1 or 0. So now we'll calculate its corresponding value of u. And we'll add and subtract a tiny amount from r being represented by epsilon. This is set to be a millionth. Then we'll calculate their corresponding values of u. Val is an accumulated value and is initially set to 0. We'll make up a loop to go through all of the terms of this derivative. We'll get all of the constants for each term. Then we'll add them onto the value. So now to get the values for the previous derivative, we'll get 2 accumulated values this time, both being set to 0. We'll make up a loop to go through every term in this previous derivative. We'll get all of the constants for each of its terms. We'll add them onto the values. Then we'll perform this numerical differentiation. This value val3 should equal val. Then we'll get the differences between these values, both the relative and absolute differences. Then we'll get the smallest difference and use that. And if the 2 values that we found aren't equal enough to each other, that is, their difference isn't small enough, then we'll print out an error message and print out these values so as to debug the code. And then finally we'll print out a message that we've finished testing this code. So this is the main difference in the testing function. We're working with different variables, but we're setting them to be different values when we're testing them. And this is the main program where we create the table, print it out and test it. And this is the function used to print out the table. We'll firstly print out y is equal to the inverse cosine, which isn't in the table, because it isn't in the form of x and u. Then we'll print out the ith derivative of y is equal to, and the indice of y here is calculated differently in this table than in the tangent table. And we'll write out the terms in algebra, using the common rules of algebra. I'll explain this function properly later. And this function prints out the table in numbers only. So this is what the table is to the first 12 derivatives. It grows at about the same rate as the tangent table, having n over 2 terms for the nth derivative. Its constants grow large, which is expected for derivatives. It's possible to store a large amount of derivatives in any computer. We could use this table to calculate the inverse cosine of any Jordan canonical matrix. So I hope that you have found this video to be helpful, insightful, exciting, interesting, and maybe even enjoyable. Please click like and subscribe if you did. Feel free to share this video. Please leave some helpful thoughts in the comments. And thanks a lot for watching.